So we have a situation here where we've got a survival function. Just like with PDFs and CDFs, it's defined for all real numbers, technically speaking, though we can oftentimes focus on a domain that's some finite interval. CDF, the survival function sigma of t is the complement of the CDF. It's 1 minus the CDF. Again, this is not a standard deviation. It's a function. Actuaries actually don't typically use this notation. They typically use the notation, well, in this context, when we are thinking about, say, a newborn baby or a new appliance, like we talked about last week, TP0, the 0 emphasizing it's a newborn, and the T is a pre-subscript, kind of strange, emphasizing that that's the variable for this function. And it's given, like you see here, to be a quadratic when t is between 0 and 30, 1 when t is less than 0, and 0 when t is bigger than 30. So in a graph, it would look like this. It would be 1 when t is less than 0. It would be 0 when t is bigger than 30. And it is constructed here to be a quadratic. You can see based on this part of the formula that's going to have intercepts at 30 and 40. All we really care about is the intercept at 30 and the fact that we just want our graph to look like a piece of a parabola. So something about like that is going to be what the graph looks like. Yes, if you continued that parabola over here, it would go below the axis and come back and have another intercept at 40. But we don't care about that part of the graph. We only really care about this part when t is between 0 and 30. And this does give the probability that the random variable capital T is greater than or equal to little t, which, since again capital T is a continuous random variable, could be thought of this way as well. Okay. Being the complement of the CDF, the limit as t goes to 0 from the left is not 0, it's 1. 1 minus 0 is 1. And the limit as t goes to infinity, well, which effectively means t going to 30 from the left here is 0, just like the CDF would approach 1 as t approaches 30. It's a non-increasing function. I asked you to verify that here. Certainly when t is less than 0 or bigger than 30, its derivative is 0. It's constant. That technically is non-increasing. It's not decreasing, but it's non-increasing. The goal here in number 2 is just to verify the derivative is negative when t is between 0 and 30. So we can go ahead and do that. Sigma prime of t. Probably best to use this expanded form. And maybe we want to even write that not as one fraction. You know, you'd have 1200 over 1200 would be 1. Minus 70 over 1200 would be 7 over 120 t squared, or excuse me, t. Plus 1 over 1200 t squared would be the expanded form of that, not as one fraction. So the derivative, take the derivative of this, you're going to get negative 7 over 120 plus 1 over 600 times t. And what do we want to do? We want to verify this is negative when t is between 0 and 30. Okay, it's certainly negative when t is 0. You might want to figure out when does it equal 0. You could set that equal to 0 and solve for t. Let's see if I can do this in my head. You get 1 over 600t equals 7 over 120. You'd multiply both sides by 600. Looks like 600 times 7 over 120. 4,200 over 120. And I don't think I can do that in my head. Does it come out nice to 35? Yeah, that makes sense since the parabola is going to have a minimum of 35. So that's where the derivative equals 0, and it's negative when t is less than that. Sigma prime of t is negative if t is less than 35, in particular if t is between 0 and 30. And there's another verification that this is non-increasing over the most interesting interval. You can use the survival function to figure out probabilities, just like you can use the CDF to figure out probabilities. So you see number 3. And by the way, I did emphasize you should write your answers as piecewise functions for these kinds of things like, well, in number 4, I guess, we're not to that point yet. You can use the survival function to figure out probabilities. So for example, the probability that t is bigger than 40 since that's a probability that t is bigger than 40, all you need to do is just plug into the survival function. Right? If you were given the CDF, you'd have to do 1 minus the CDF value. But the survival function is already the complement of the CDF. So you can just plug into the survival function. Although 40 is past the domain where the PDF is positive, or the survival function is positive, we are at 0 here. More interesting is the probability that t is bigger than 20. That'll be sigma of 20. And we can use any one of the formulas that we have. Probably easiest to use this one. So we have 30 minus 20 is 10 times 40 minus 20 is 20 over 1200. That'll be 200 over 1200, 1/6 would be the probability that t is bigger than 20, for example. The probability that t is less than or equal to 10, you'd want to do just 1 minus the survival function, effectively using the CDF. In 4, we're after the PDF, the CDF, and that's not a mean, right? Confusing notation. This is a force of mortality. Actuaries use the letter mu here because mortality starts with M, just like mean starts with M, unfortunately. For the PDF, maybe I should move this down so it focuses better here. For the PDF, it's the derivative of the CDF, so it's the opposite of the derivative of the survival function. And let's only worry about this when t is between 0 and 30. It's 0 when t is less than 0 and 0 when t is bigger than 30. It's technically not differentiable at 0 or 30, actually. We've already figured out the derivative. It's right there. Just take its opposite, and that'll be your PDF when t is between 0 and 30. 7 over 120 minus t over 600. You could get a common denominator if you like. You could also write this as 35 minus t over 600. Again, when t is between 0 and 30. You're not asked to confirm that the integral of this from 0 to 30 is 1, but you could. Maybe you want to do that quickly on Mathematica. Let's just confirm that the integral of this function from 0 to 30 is 1. So it is a valid PDF. There we go. CDF is 1 minus the survival function. Capital F of t is 1 minus sigma of t. Once again, let's just focus on when t is between 0 and 30, though again, I asked you to think about piecewise definitions for all t as well. So we just take 1 minus this thing. Maybe it's easiest to think about doing 1 minus this when I split the fraction apart into pieces. 1 minus this thing. So the ones will cancel, and the other ones will have their signs changed. So we get positive 7 over 120t minus 1 over 1200 t squared when t is between 0 and 30. Finally, the force of mortality, mu of t, by definition, that's the relative rate of decay of the survival function, negative sigma prime of t over sigma of t. There's sigma prime. Right there. 35 minus t over 600. Oops, that's F, sorry. I want the opposite of that. t minus 35 over 600. But I am putting a negative sign in front of this whole thing. So I can bring the negative sign up at the top there. Then divide by sigma of t. I won't bother taking the time to simplify this. Sigma of t. You can use any one of these forms. You get fractions within fractions initially, but it can be simplified. What domain would be of interest here? I'll let you simplify that. 0 to 30. And actually, this function is undefined at 30. It actually has a vertical asymptote there. This when t is between 0 and 30. It turns out if you graph this function, it's got a vertical asymptote at 30. It looks about like this. Okay. What is this representing again? This is representing the survival of, well, hopefully not a person. We don't want people to just live to 30 years old, but say an appliance. Maybe the appliance has got some built-in circuit that kills it when it reaches 30 years old. Can't live past 30 years old. Okay. The fact that what does the PDF look like? What does the graph of the PDF look like? Here's the PDF formula. The graph of that PDF is a linear function with a negative slope looking about like that. Intercept would be 35 over 600. It's a probability density function where it's higher. If you're imagining doing simulation here with data, maybe putting this into Mathematica in some way, which you actually can, using random variate to simulate sampling from this distribution, the data is going to be denser where the PDF is higher. When you use the PDF to find probabilities, you're finding areas under the PDF, and they will be certainly higher over, say, an interval of length 5 when t is small compared to an interval of length 5 when t is larger. So you get a higher probability that the lifetime of this appliance is going to be in the low range than in the high range. What does that mean in terms of the force of mortality? I don't know if you remember this. Again, the force of mortality by definition is the relative rate of decay of the survival function. This is a positive quantity because the derivative is negative. You can also interpret it as helping you approximate a certain conditional probability. I didn't explain this, and I'm not going to take the time to explain it either today. Imagine that newborn appliance, okay, right off the assembly line or whatever, it's about to be sold. And you're sitting here wondering about its future lifetime, and you're saying, you know, if I assume this appliance makes it to 29.9 years old, and you know it's got a chip in it that's it's gonna make it drop dead by age 30, what is the probability that it lives for another day if I assume it makes it to 29.9 years old? It's going to be a much higher probability of dying in the next day if it makes it to 29.9 years old than if it's just been sold. The force of mortality times the length of time of a day being 1/365th of a year would give you an approximation to the conditional probability of dying in the next day if it makes it to 29.9 years old. I'm not explaining that, but it can be interpreted that way, it turns out. The force of mortality for actuaries is useful for modeling. We talked about also how to try to go backwards. You can use this equation to figure out sigma, recognizing that this thing is really the negative derivative of the natural log of the survival function, effectively integrating both sides after also multiplying both sides by -1 and then exponentiating. In the end, you can figure out the survival function if you know the force of mortality with this equation. And I forgot the negative sign right there. Okay, so that's a common thing that actuaries do is they model with mu of t. And once you've got mu of t, you can figure out sigma of t, survival function. 1 minus that is the CDF. The derivative of the CDF is the PDF, and you can go from there. We also, as always, talked about moments in these kinds of situations, first and second moments, and then using the second moment and the first moment to figure out the variance and standard deviation. And you have these formulas, including right? The Darth Vader formula that helps you figure out the first moment of t in a new way that possibly could be easier. By definition, if t is a non-negative random variable, as it is with these survival functions, we don't have to integrate from minus infinity to infinity. We can integrate from 0 to infinity. T times the PDF will give you the mean, but yes, the Darth Vader rule says you can actually just integrate the survival function. And for the problem at hand, you can get away with an integral from 0 to 30. Because the survival function's 0 after we reach 30. Let's go ahead and use Mathematica to see what you should have gotten for that. So integrate the survival function from 0 to 30. Survival function being, again, I'll write it in this form, 7t over 120 plus t squared over 1200. That should be the mean. 45/4 should be the same thing. You might want to double check if we did it as t times the PDF. T times PDF is the 35 minus t over 600. Should get the same answer here, hopefully. We do. 45/4, 11.25 is the mean of t. For the second moment, here's the definition of the second moment. Do that integral. But the Darth Vader rule applied to the second moment says you can also integrate, let's see, 2t times the survival function. I copied and pasted the wrong thing. 2t times the survival function. This should give us the same answer. Yay. As usual, take your second moment, subtract the square of your first moment. What was it, 45/4? There's your variance. Take the square root of that. Standard deviation is about 7.8. Okay. I also learned a little bit about the Curtate random variable. I think I want to skip that. I won't test you on it. I hope it made sense anyway. Because I think with the time we have remaining, I want to go on to the next handout and now relate this to the time value of money ideas that we talked about at the end of class on last Thursday. So we're still doing the same example, still the same situation. I'm not going to talk about the client right now either. I will probably talk about that still, though, with the second handout. So here we're talking about the time value of money as well. Okay. And what are we really after here? We're after what's most often called actuarial present value. In the handout, because this was what my teacher did 20 years ago, I called it net single premium, NSP. NSP stands for net single premium APV stands for actuarial present value. Actuarial, can I spell that? Actuarial present value. And these are actually the exact same thing, at least in this context. I'll talk about the time value of money, but let's just think of it in terms of, say, life insurance, whether for a person or for an appliance, which then would be really a warranty, say. You've got your survival random variable, capital T, okay, that you could use different models for. You could use a uniform model. You can use an exponential model. You could use the model we're using on handout number 1, this quadratic model for the survival function. not specifying the model here. Okay. From this, we'd like to create a new random variable that, unfortunately, once again, with notation, we use something that's confusing because we have another meaning for this. We use the letter Z for it. Actuaries use the letter Z for it. This is not a standard normal random variable. Another confusing thing is they put a bar above it, which is doubly confusing, as we're going to see very soon once we get to chapter 6, because when we put a bar over a random variable once we get to chapter 6, it's always going to mean something called a sample mean. So it's doubly confusing. But it's what actuaries do. It's like they're purposely setting out to confuse you. No, they're not really, but they have their own idiosyncratic notation. They're not trying to make life confusing. They're trying to make, for them, life less confusing. But to the uninitiated, it's like, oh man, this is really confusing. It's confusing for sure if you don't know any problem stats, but even if you know problem stats, it's confusing because it's inconsistent with notation and problem stats. What is this random variable going to be? There's a couple different ways to write it. One way I write it in the handout is v to the t power. Another way to write it is e to the negative delta times t power. What in the world is this all about? Now, if you remember from last Thursday, v is 1 over 1 plus I, where I is the interest rate that you're using to model the time value of money. I is not the imaginary unit, it's the interest rate, say annual to keep it simple, interest rate to model the time value of money. Now, what does that mean I would be in real life? You know, different investments have different rates of return. And you also have complications like the stock market goes up and down, right? It's not a steady rate of return. It's simplest to imagine this in terms of savings account because your interest rate is usually pretty steady, though often very small in the last 30 years. Going up a little bit now with inflation going up. So it's confusing. What should I be? We're not really worried about that. We're just saying, pretend you can model the time value of money with some interest rate I, meaning, as I talked about last Thursday, that $1 today, that's a dollar symbol there, is equivalent to 1 plus I to the t power dollars t years from now. If I is 0.04, like I think it is in handout number 2, this would be 1.04 to the t. If t is 1, then it equals 1.04. Effectively, you're saying $1 now is worth the same as $1.04 1 year from now. Of course, that's a bigger deal if you're talking about larger values of money. $1,000 today is equivalent to $1,040 1 year from now. And when you're talking more than 1 year from now, like 10 years from now, 1.04 to the 10th power is not, it's not 1.4, right? It's bigger than 1.4, a little bit. So $1,000 today is equivalent to, at this 4% annual interest rate, $1,480 10 years from now. So it gets more significant over time, and it gets much more significant when you have a larger interest rate. We're talking about a 10% interest rate, say for 50 years. $1,000 today at a 10% interest rate is equivalent to $117,000 50 years from now. If you're going to apply this in real life, you got to imagine you can actually find investments where you get that kind of rate of return, which again, maybe you can get that in the stock market over the long haul, but over the short run, the stock market goes up and down a lot. This statement can also be written as $1 t years from now, $1 t years from now is equivalent to 1 over 1 plus I to the t dollars today. Today. Can't spell today. That's a t there. Which, if I've defined v to be 1 over 1 plus I, that's the same as v to the t. So coming back up here, if t is your time of death, say, or the amount of time you survive is the more positive way to say that, and your beneficiary, your spouse, say, is going to be paid $1 t years from now. Imagine you're a newborn baby and your parents get an insurance policy for you. V to the t represents, as a random variable, the present value of that future $1 payment. You know, if you survive to 80 years old, this is going to be a very small number. The observed value would be very small. Maybe 0.1 or maybe even smaller. That would be the observed value of z bar if the observed value of t is very large. On the other hand, if you die when you're very young, but your parents still took out an insurance policy, then the $1 present value now is not so small, maybe 0.9. What's delta? Well, delta is chosen so that v equals e to the negative delta. In other words, negative delta is the natural log of v, and that's equivalent to delta being negative natural log of v. Bring that negative sign up into the power by property of logs, and that's the same as the natural log of 1 plus I. If you have exponential growth in the time value of money, if this 1 plus I to the t is an accurate model, I really is the interest rate, annual interest rate, say. Delta is the instantaneous interest rate, you might say, or the continuous interest rate. It represents the instantaneous relative rate of growth. Probably learned about that in calculus a little bit. Actuaries commonly use capital A for their amount function, they call it, representing the amount of money you have at time t. And what this is really is the derivative of A divided by itself. It's a relative rate of growth of the amount of money that you have. And if it's exponential growth, that's going to be constant. That's something you should have learned in calculus. First couple weeks of calculus, maybe even pre-calc. Well, okay, no derivatives in pre-calc, sorry. Okay, you modeled exponential growth. Okay, so that's a new random variable. What do we want to know about it? The typical kinds of things. It's mean and variance and standard deviation. So you got to find its mean and its second moment. I don't talk about this in the handout, but we also might be interested in its PDF and its CDF. We might be interested in those too. Let's talk about what's in the handout first. What's its expected value? What's the expected value of z bar? And do actuaries have a name for that? Yeah, they call it A bar. I think the A, when they use an A there, they're thinking actuary. They're like naming it after actuaries, in honor of actuaries. That's my guess. I've never asked anybody. But I think they're thinking actuarial present value there. Yeah, this is an actuarial present value, or like I talk about in the handout, a net single premium. What in the world? Why these different names? Well, it is related to actuarial science, so this kind of makes sense. It is, in a sense, a present value because z bar is a present value. Z bar is the present value of $1 paid t years from now. Imagine there's a 1 being multiplied in front of us. Z bar is the present value of $1 paid t years from now. 1 times v to the t. It is a present value. We're calling it an actuarial present value because now we're taking its mean. And what's more important for actuaries is the mean, because when you have an insurance company, you want to have lots of customers, right? You don't want to have just one customer. That would be bad, because when that one customer dies, you go broke. You want to have lots of customers who are paying lots of premiums for a long time so you can build up your reserves. And then when one out of your 1,000 customers dies, you're able to cover the losses, is the general gist of what you want to think about. Being such a present value and a mean of a present value random variable, it's also called the net single premium, essentially because it's like meant to be the fair price that they should charge the parents for the newborn baby who are buying insurance for the newborn baby at that time, because the present value should be equal. They're paying, maybe the present value is small for $1 future payment. It's like 0.1 or something. They should pay the insurance company 10 cents to get that $1 benefit in the future when that person dies. Of course, the parents probably won't get the benefit. It'd be maybe the spouse or something, but to equalize, what is the insurance going to do with that 10 cents? They're going to invest it, hope it grows. Of course, this is ignoring complications. This is ignoring complications like, well, this insurance company's got expenses. They have other customers. They have other payouts. They also want to make money. They want to make a profit. They also have to like give themselves some cushion, hedge their bets. This is sort of just the simplest way to think about what's the fair price, but they're probably going to charge you more. It would be a bad insurance company if they didn't charge you more. Anyway, it's the expected value of Z bar, which, since Z bar equals this, is the same as the expected value of e to the negative delta times t. And so that's going to be the integral from 0 to infinity of that function. Replace the random variable with an ordinary variable times your PDF. But this could be written in terms of the survival function of t as well, as actuaries tend to do. You could replace f of t with negative sigma prime of t, right? Remember, sigma of t is the survival function. It's 1 minus the CDF. So it's the negative of the derivative of sigma of t that is the PDF. Okay? And so that's the integral you do to figure this out. And your homework, you have to do an integral like this. What about the second moment? Expected value of z squared. What's the actuarial notation for that? It gets weirder. A bar with a pre-superscript 2. Oh. Sorry. On Moodle, I have, a picture of actuarial notation, and yeah, there are post subscripts and superscripts like we're used to, and there are pre-subscripts and superscripts all in one symbol. Okay, this is just the beginning. That's their symbol for the second moment of Z bar. Sometimes forget the bars. The bars are actually supposed to refer to the fact that this is a continuous model. With discrete models, they don't put the bars there. I think they're thinking about a line being continuous, but it has nothing to do with means, as we'll learn about in chapter 6. Well, or not directly, at least. It's not the exact same idea. I mean, these things are still expected values, so in a sense, they're still means, but not these thing that we're going to learn about in chapter 6. So that's the expected value of e to the negative delta t squared. Hey, but by a property of exponents, that's the same as the expected value of e to the negative 2 delta times t. And so we effectively do the same integral, except we replace delta with 2 delta. And that's kind of a special thing based on the fact, this property of exponential functions, that this happens. And if it's not clear, we are multiplying here. We're not doing a literal subtraction. That's why I'm using the parentheses. So you do that integral. Okay. We're not focused on completely understanding everything here. We're just trying to kind of get you used to what's going on here. A little used to actuarial notation and going ahead and doing these calculations. We're not trying to understand this fully by any means, okay? Another important application that comes up in the handout. This is when we're thinking about these things, and again, you'd also want to find the variance and standard deviation from this in the usual way. When we're thinking about these things, it's also important to think about not only what do you benefit from the insurance company when your spouse dies, say, or when from the warranty when your appliance fails, but also, especially with insurance, you want to think about premiums, money that you are paying to the insurance company, typically every year. That's going to have a present value as well. We might be interested in that random variable as well. To talk about that, in handout number 2, I have to start with a non-probability topic, the concept of an annuity, present and future values of annuities. And what I talk about is something called an annuity due. I don't use the word due in the handout, but I'm using it here. There's also another concept called an annuity immediate. I think the terminology there is a little strange, but I'm not going to go into details. Imagine a number line representing time. It's a timeline. And you're going to make payments at certain moments of time. Keep it simple, say integer values of t. Now, it's easiest to pretend time is in years. So I'll go ahead and do that. With insurance premiums, it's possible you might have to pay every month. Okay, but it's going to be simpler if we just imagine you pay once a year. And once again, to keep it simple, just like we're imagining that future benefit to be just say $1, even though of course it'd be more. Let's imagine your premium payments are $1 as well. Starting right now, today, time 0. That's what makes this an annuity due instead of an annuity immediate, but that's confusing because that's immediate. Okay, I don't want to go into the details. We're going to have n payments. So the last payment is going to be at time n minus 1, not time n. These are n payments of $1, of $1 each. I could ask, what's the present value of all these payments right now at time 0? Present value of all these payments. And as always, there's a funny notation for this. A sub n in these little brackets and double dots above it. Ugh. Now, if you know a little physics, you might be thinking those double dots are like a second derivative or something. No, they're not. I don't know the origin of the double dots. It's related to the fact that it's annuity due instead of annuity immediate. And again, I'm not talking about what an annuity immediate is. With the annuity immediate, they don't put the double dots there. Don't worry about the notation. I'm not really testing you on the notation other than to say, do this. The present value of the first payment at time 0 is just itself. It's 1. The present value of the second payment at time 1, what is it? Well, it's $1 at time 1. So its present value 1 year before that right now would be v to the first. Yeah, just v. Or 1 over 1 plus I if you prefer. 1 plus I to the negative 1 power. What's the present value of the payment at time 2? It's got to go back in time 2 years to the present. Its present value is v squared. Etc. The last $1 payment at time n minus 1 is going to have present value v to the n minus 1. This should look warming to your heart. Calculus 2, geometric series. Oh, it simplifies. Oh, but we got to remember, what's the formula for the sum of a finite geometric series? Actually, a sum of an infinite geometric series is simpler, right? You remember that? It's A over 1 minus R is how it's often written, where A is the first term and R is the common ratio. The common ratio here is V. Okay, with a finite geometric series, I always remember the formula in words first. I remember it as the first term times 1 minus the common ratio to a power equal to the number of terms, all divided by 1 minus the common ratio. That's how I remember it. And then the letters that you use depend on the situation. The first term is the 1. Oops. 1 times 1 minus the common ratio is the V. The V is what I need to multiply each term by to get the next term. V times 1 is V. V times V is V squared. V squared times V is V cubed. What's the number of terms? There were n payments. Starting at time 0, the last one at time n minus 1. This power is n, not n minus 1. All divided by 1 minus V. This can be written in terms of I. Here's one way to write it. Because V equals 1 plus I to the negative 1 power. You could think of those as fractions if you like. You could multiply the top and the bottom of this by 1 plus I to the n if you wanted to. It's not necessary to. There are various kinds of ways you could write it. So if you know what I is, you can figure this out. I think in the homework, I is 0.04. Let's pick something else like 0.08. Pick something for n like 10. We could figure out V is 1.08 to the negative 1 power. 1.08 to the negative 1 power, about 0.9259259. I guess that's a repeating decimal, yep. Looks like the 259 repeats. If I want to use this formula, what would I do? I'd raise it to the 10th power, say first. Subtract that from 1. 1 minus that. And then divide by 1 minus the 0.9259259. Looks like the present value is about 7.25. So A double dot sub 10 in this context is about 7.25. Does this answer make sense? What in the world is this telling us? It's telling us that at an 8% interest rate, the present value of these 10 payments of $1 starting at time 0 and ending at time 9 is less than $10. You're getting paid $10 total. 10 ones in nominal dollars, you might say. But in terms of thinking about the time value of money, that's worth less than $10 right now. It's worth $7.25 right now. Another way to think of this is if you paid somebody $7.25 right now, because you were aware that there's an 8% interest rate available, that would be equivalent to getting these $1 payments back at these times. You wouldn't be gaining any money effectively. You'd be breaking even because you paid them that much. If you paid less than that, then you'd be getting a gain. Question?
Is that what they do with the lottery jackpot? They say,
Yeah,
they this much now.
Yep.
I'll give you this much a year for so many years.
Yeah, if you win the lottery, you can get your payment in one of two ways. You can either get a lump sum payment like right now,
so
or
instead of $1.7
so much.
billion, I only got $600 million.
Right. This, yeah. But the benefit of getting the lump sum payment, as long as you don't spend it right away, is you could invest it. Of course, there's tax implications and things like that that I think complicate matters.
Most people take the lump sum down.
Do they?
Yeah.
Yeah.
I think they want it right now. They trust it.
Yeah, they want to spend the money right now.
Give it to me right now. And a large fraction of those people, couple years later, have nothing left.
Yeah.
It's gone.
Yeah, maybe from their relatives, right? They're giving money to their relatives and their long lost friends from high school that they don't remember even. It's also important to think about future values. Think about how your investment might grow. We could also think about the value of these payments at some other time, like time n. What's the future value of all these payments at time n? The notation for that is S sub double dot n. We're not really going to focus on that for the homework, but just for the sake of completion. Here you raise 1 plus I to positive powers because they're going into the future. This first payment at time 0 goes into the future n years. So its future value is 1 plus I to the n. The second payment goes into the future n minus 1 years. So its value is 1 plus I to the n minus 1, etc. The last payment goes into the future 1 plus I years. So you can use formula for the sum of a finite geometric series again to figure out a simpler formula for this. That's not what I really emphasize though in the homework. How is this related to probability? It's related to probability because these payments and actuarial science, these payments, well, if it's a life insurance policy, you don't know when the person is going to die. You don't know how many payments they're going to make to you as the insurance company. So this annuity itself has a present value that's a random variable. And we'd be interested in things like means and variances of that. I get into that in the very last part of the handout here, but it's the most confusing part of the handout. So I think I'm not going to assign that. Realize I did something that's not ideal here. If you read it, I define this quantity m to be the greatest integer in t if t is not an integer, and t minus 1 if t is an integer. Effectively, what this summation represents is the present value of an annuity based on dying at time t, premiums you're paying to your insurance company. If you die right on your birthday, t is an integer, well, you only paid a premium payment up through your last birthday, effectively, is what this is saying. If you die halfway between one birthday and the next, or not even halfway, a quarter way or whatever, your last premium payment was at your last birthday. You're making premium payments at your birthday to keep things simple. Here's the idea. And you can plug in capital T as a random variable here and get a new random variable. It's a little confusing. I'm not going to assign anything about that, but just trying to make you aware. You should, though, for the sake of just completion, be able to compute these things. But this is not probability and statistics here. This is just financial computations. But I think it's worthwhile for you to do it anyway. So I will assign problems like that.